Good morning, everyone, and welcome back to the channel. Today, we're continuing our deep dive into one of the most fascinating engineering subjects in the oil and gas industry, the construction of an offshore oil platform. Now, if you think about it, the ocean is one of the most unforgiving environments on the planet. Extreme weather, corrosive salt water, crushing depths, and yet humanity has found a way to build permanent structures out there. Structures that extract millions of barrels of oil and gas every single day. It is genuinely a remarkable story of engineering. We've already covered chapters 1 and 2 in previous videos, so if you haven't watched those yet, the links are down in the description. Make sure you catch up before going further. Now, into this video, we're going into section 1, and we'll have 3 key topics on the table. We'll be starting with the introduction, then moving into planning and design, and we'll round things off with fabrication and module construction. It's going to be a very insightful session, so make sure you're comfortable, grab something to write with, and let's get into it.
Welcome to today's Explainer. Get ready, because today we are taking on a topic of absolutely staggering proportions. We're looking at the sheer scale of offshore oil platforms, structures that literally rival skyscrapers in height and weigh tens of thousands of tons. It's a mind-boggling level of complexity. We're going to break down exactly how these mammoth structures go from just a simple idea on paper to a colossal reality, all while battling some of the harshest conditions on planet Earth. Okay, let's dive into this. Just think about the sheer audacity of this entire concept. How do you actually build a heavy industrial facility right in the middle of a hostile ocean? We're not just talking about dropping a heavy block into the water here. We're talking about constructing what is essentially a fully self-contained industrial city miles from shore, where the environment is actively working against you every single second. This monumental engineering and logistical challenge is going to frame everything we look at today. To make sense of this massive project, here is our roadmap. 1. The ultimate engineering challenge. 2. Fixed versus floating platforms. 3. The platform lifecycle. 4. Managing high-stakes risks. And 5. Tech, environment, and future. Section 1. The ultimate engineering challenge. Harsh marine settings. To really grasp this ultimate challenge, we kind of have to shift our mindset right out of the gate. These aren't just static buildings. They are immense, highly dynamic facilities that have to juggle active drilling, volatile hydrocarbon processing, and high-density living quarters, all at the exact same time. And they're doing all of this while constantly absorbing severe environmental loading. I'm talking crushing waves, howling winds, and incredibly corrosive saltwater. It makes it one of the absolute most demanding operational environments in all of contemporary engineering. Now, what's really interesting about this slide is how it demystifies where the action actually happens. Because while the topside platform, the part above the water, is the most visible element, the true magic often happens far below the surface. Subsea systems are this critical, highly pressurized underwater infrastructure. They physically bridge the gap between the deep-sea reservoir, which is buried way down beneath the seabed, and the host facility floating or standing way up above it. It's a total engineering marvel, safely channeling all that energy right through a highly volatile environment. Section 2. Fixed versus floating platforms. Anchored or riding waves. Because the ocean varies so wildly from place to place, engineering solutions have to be highly specific. So the very first major design hurdle is, do we anchor this thing to the seafloor, or do we let it float? Over on the left, you've got fixed platforms, like your traditional jackets and compliant towers. These are pinned directly into the seabed, usually maxing out at around 400 to 500 meters deep. But if you go beyond that, floating concepts have to take over. We're talking massive semi-submersibles, cylindrical spars, and tension-leg platforms. They are moored really tightly to the seafloor, but they actually ride the deep water column. So what does this all mean for the engineers? Well, making that choice comes down to 4 major variables. First up, water depth. Absolutely dictates whether a fixed or floating concept is physically even possible. Second, seabed conditions. Determine the exact type of anchoring or foundational support you're going to need. Third, meta-ocean characteristics, which is basically a fancy way of saying local storms, wave heights, and weather patterns. Those completely influence the structural strength required. And finally,
reservoir requirements affect the overall size and processing layout. So every single facility is a brilliant, completely custom response to its entirely unique marine environment.
Section 3. The platform lifecycle. From concept to ocean. Let's move to and see how this builds, because taking a project from a blank page to a producing giant is an incredibly choreographed dance. It begins with millimeter-perfect detailed design, which feeds directly into the massive structural fabrication of thousands of tons of steel in shipyards. Once built, these absolute behemoths face complex marine transportation across the ocean for precise offshore installation. Only then does the intricate task of systems integration begin, finally culminating in final commissioning to ensure absolute operational safety. But here's the thing, the life cycle absolutely doesn't end when the oil starts flowing. Maintaining these structures against a corrosive ocean is a constant, carefully planned battle. Long-term asset assurance relies heavily on strict materials selection from day one. From there, you need continuous corrosion protection and just relentless inspection and integrity management. You have to remember, the ocean literally never stops trying to tear these platforms apart. So keeping them safe and operational until their eventual decommissioning or life extension is just as complex as building them in the first place.
Let's turn to Section 4, Managing High-Stakes Risks. Execution Complexity.
When you're dealing with projects of this sheer magnitude, the volume of things that can go wrong, the cascading risks, is pretty staggering. I mean, geotechnical uncertainties on the seabed can instantly disrupt your foundation plans. Then, those delays collide with severe weather constraints that can halt marine logistics for weeks at a time. Add in strict fabrication quality control, constant safety hazards, and the absolute headache of coordinating multiple contractors across different global work fronts simultaneously, and you have a monumental task just to keep the plate spinning safely. The invisible force preventing this whole thing from descending into chaos is rigorous project governance. When you're dealing with multi-billion-dollar megaprojects, a single logistical delay can cascade into massive cost overruns. So relentless cost control and strict schedule management are the absolute glue. They're what ensures these thousands of moving parts actually align and execute safely.
Finally, Section 5, Tech, Environment, and Future. Digital Revolution. And this brilliantly illustrates how modern offshore engineering isn't just standing still. Digital technologies and automation are absolutely revolutionizing how these megastructures are built and maintained. From incredibly advanced design coordination using digital twins to radically improving subsea inspection efficiency with drones, going digital is making these platforms so much smarter, safer, and far more reliable throughout their entire life cycle. To sum up the incredible scope of our source material today, consider this quote: "The successful delivery depends on the effective integration of engineering rigor, risk management, environmental stewardship, regulatory compliance, and life cycle planning." I think that perfectly captures the core takeaway here. Building an offshore platform isn't just about bending huge pieces of steel. It's an incredible, delicate balancing act of human ingenuity, unyielding safety standards, and deep environmental responsibility. Which leaves us with a fascinating final thought. We've seen the sheer determination and structural brilliance required to place these sprawling industrial cities out in the sea. But as we push for even greater sustainability, tighter regulatory frameworks, and rapid digital automation, how will these massive ocean giants evolve in the future? Could they eventually become fully autonomous? Only time will tell. Thank you so much for joining me for this explainer. Keep questioning, keep learning, and I'll see you next time.
Welcome to the quiz section, Fastest Finger Edition.
Please like, share, and subscribe to Master Sense by Faraday, and turn on notifications so you don't miss new and upcoming videos.
Welcome to today's Explainer. Have you ever looked at one of those massive offshore platforms just standing absolutely defiant in the middle of a raging ocean and thought to yourself, how on earth did they actually build that? Well, the truth is, long before a single piece of steel is ever cut or any massive cranes are deployed, there is this totally invisible, monumental intellectual effort that takes place behind the scenes. So today, we're going to unpack the incredible engineering design and structural planning that makes these modern maritime marvels even possible.
To help us navigate all this, here is our engineering blueprint for today. We're going to start by sizing up the ocean. Then we'll meet the engineering dream team. After that, we'll walk through the 3 steps to design, see exactly how they go about surviving the elements, and finally, break down the difference between fixed and floating systems.
All right, let's jump right in. Section 1, Sizing Up the Ocean, the Hostile Environment.
So, the absolute most crucial question we have to tackle right out of the gate is, how do you outsmart the ocean? I mean, the stakes here literally couldn't be higher. We are talking about surviving some of the most extreme, unrelenting environments on planet Earth. And to win that battle, engineers have to meticulously map out the battlefield long before the construction process actually begins.
Well, it all kicks off with a phase called site characterization. This is the initial evaluation of extreme environmental elements. We're looking at things like water depth, seabed stratigraphy, which, by the way, is really just the industry's fancy way of saying the physical layers of the seafloor, and soil strength parameters. Think about it. Just like you wouldn't build a towering skyscraper on soft mud, you absolutely cannot drop a multi-thousand-ton rig onto a weak seafloor. All of this initial data is vital because it directly informs the concept selection, the foundation strategy, and the preliminary design criteria. You simply can't build a permanent solution until you fully map out the exact seabed you're building on. But listen, it's not just the soil they have to worry about. Oh no, engineers must account for wave climate, current profiles, intense wind loading, and constant corrosion exposure. Because, let's be real, salt water essentially exists just to eat steel. And if that wasn't enough to keep them up at night, they also have to calculate for seismicity, earthquakes. The sheer volume of extreme forces engineers must account for right from day one is just staggering. They aren't just designing a building here, they are designing an unshakable fortress built to withstand constant, multi-directional assault from water, wind, salt, and even the shaking earth itself.
Moving on to Section 2, the Engineering Dream Team, Multidisciplinary Effort.
Now, pulling this off, that definitely doesn't just come from one type of engineers sitting alone in a cubicle somewhere. Conquering these insane conditions requires highly multidisciplinary teams. We are talking about structural, marine, and geotechnical engineers laying the literal groundwork, working alongside mechanical, electrical, instrumentation, and process engineers who bring the facility's complex nervous system to life. The sheer scale of human expertise required to develop the technical basis for this kind of facility is honestly mind-boggling. Everyone brings their own highly specialized piece of the puzzle to make sure this massive structure operates seamlessly under immense pressure.
So, why does all this matter? Well, those intense design calculations, load cases, general arrangements, and equipment specifications, they aren't just some academic exercise in structural physics. They directly translate into life-saving safety provisions. We're talking robust fire protection, rapid emergency shutdown mechanisms, and completely secure evacuation routes. At the end of the day, all of this complex math is ultimately about human survival. It's about ensuring that in a worst-case scenario, people can get out safely and our fragile marine environments are strictly protected.
Okay, Section 3, 3 steps to design, the master sequence.
So from a technical perspective, how does a rig actually go from an idea to reality? Well, it generally follows 3 definitive steps. First up is concept selection, where the broad ideas are established based on all that crazy site data we just gathered. Second is front-end engineering design, or what the industry calls FEED for short. That's where the chosen concepts start actually turning into concrete plans. And third is detailed design. It's this beautiful, systematic evolution of a rough napkin sketch into a highly granular blueprint where literally nothing is left to chance.
Next up, Section 4, Surviving the Elements, Stress Testing the Reg.
Okay, to mathematically guarantee survival, engineers do two very distinct tests. First up is global structural analysis. This is where they mathematically crash massive, rogue waves against the entire virtual structure. They evaluate the whole platform's response under gravity loading, wind current, potential vessel impacts, and seismic excitation. But then, they zoom way, way in for local analysis. They take all those massive global forces and apply them to a single critical joint, a tiny brace or a lifting point, just to see if a microscopic weld might fail under the pressure. It's this really dramatic shift from making sure the entire fortress can stand up to a hurricane, all the way down to ensuring the tiniest structural detail won't snap.
And finally, Section 5, Fixed versus Floating Systems, Structural Strategies.
Now, depending on the actual location you're building in, the engineering challenges completely flip. In fixed platforms, the steel legs, or jacket members, lock rigidly to the seabed. So particular emphasis is placed on the interaction between these members, the piles driven deep into the earth, and the seabed materials to ensure reliable load transfer and long-term stability. But if you move out into deep water, floating systems are required, and the whole dynamic shifts entirely. Out there, the analytical focus extends to hydrostatic stability and mooring performance, basically anchoring the rig while allowing it to dynamically dance and react to the waves, rather than stubbornly fighting them. So, after all the site characterization, the calculations, the global and local zooming, and deciding between a fixed or floating rig, what's the actual result? Well, these evaluations give us the precise member sizing, they calculate the exact total steel tonnage required, and they map out the specific foundation configuration. The combination of this massive intellectual battle mathematically guarantees that the design works, long before a single piece of steel is ever ordered or a welding torch is ever fired up.
And that brings us to one final, pretty profound question. What actually guarantees the expected integrity of the platform throughout its entire life? Well, it's not magic, and surviving the brutal ocean is certainly never a matter of luck. As we've seen throughout today's explainer, that integrity is the direct result of this extraordinary, invisible phase of structural planning and relentless engineering. Every single wave, every gust of wind, and every layer of sand is meticulously accounted for before construction even begins. So the next time you see a picture of an offshore rig standing tall out in the middle of nowhere, just think about the sheer mountains of math and human ingenuity that got it there. Kind of makes you wonder, what other invisible engineering marvels are hiding in plain sight around us every single day?
Welcome to the quiz section, Fastest Finger Edition.
Welcome to this explainer, where we're going to dive right into the absolute engineering marvel that is offshore oil platform fabrication. I mean, we're talking about structures of almost unimaginable scale and complexity here, designed to operate in some of the most unforgiving environments on the entire planet. Let's jump in and uncover the engineering secrets that make building these things even possible. So let's start with a pretty obvious question, right? How exactly do you construct these absolute behemoths out in the middle of the crashing waves and crazy unpredictable weather? You know, when we see pictures of these giant platforms standing tall in rough seas,
You kind of assume there's this massive fleet of ships and brave workers out there piecing it all together beam by beam, just battling the elements the whole time. Sounds totally impossible, doesn't it?
Well, the surprising reality is you don't. You actually build it on land. In practice, offshore oil platforms are almost entirely fabricated in specialized onshore construction yards. They aren't just built out there in the water. This one fundamental shift in perspective basically changes everything about how we understand these megastructures. By keeping the construction on solid ground, engineers can essentially take back control from the chaotic marine environment.
Okay, moving on to Section 1, Anatomy, Jackets and Topsides. To really get how this onshore construction works, we gotta break the platform down into two totally distinct worlds. For fixed facilities, the underwater foundation is what we call the jacket. Picture a really intricate lattice framework made entirely out of tubular steel members, meticulously designed to eventually sit right on the seabed. Now, at the exact same time the jacket is being built, the section that actually sits above the water, which we call the topsides, is also coming together. It's kind of like, well, think of the jacket as the sturdy legs and the topsides as the brain and body of the whole operation.
And let me tell you, those topsides are incredibly complex. They aren't just empty decks. They're fully functional, highly specialized modules. Based on our source material, the systems packed into these things are just astounding. We're talking drilling systems, separation equipment, massive compression units. And it doesn't stop there. You've got power generation, heavy-duty pumps, the actual accommodation blocks where the crew lives, high-tech control facilities, towering cranes, flare equipment, and literally all the utility services. It's basically a self-sustaining industrial city, all packed into a modular footprint. Crazy, right?
So how does the underwater foundation actually come to life? Well, building the jacket follows this incredibly precise sequence. Step 1. Steel plates are expertly cut, formed, fitted, and welded. And we're talking strict adherence to approved procedures here. Once those pieces are prepped, step 2 is assembling them into specific components. So your legs, your braces, and the supercritical connection points, which are called nodes. Finally, step 3, all these individual sections are integrated into the massive structural frames that will eventually take the plunge into the ocean depths. Which leads us perfectly into Section 2, the modular advantage. So why do we do it this way? Why build everything conceptually, like snapping together a massive high-stakes Lego set on land? Well, because yard-based construction gives you these absolutely crucial advantages that you just can't get out at sea. The teams get rigorous quality assurance and essentially laboratory-level control over the welding. Plus, you get reliable schedule management away from crazy ocean storms, and this is a big one. It drastically improves occupational safety for the workers building it. And it's exactly because of those yard-based benefits that the topsides are frequently modularized. The whole goal here is to maximize the amount of equipment installation and systems testing that can be finished entirely onshore. I mean, just imagine trying to test a highly sensitive compression unit or trace a tiny electrical fault in the control facilities while you're pitching back and forth on 40-foot ocean waves. No thanks. By modularizing the topsides, engineers make sure that when the platform finally heads out to sea, everything is already tested, fully integrated, and 100% ready to go.
That brings us to Section 3, zero margin for error.
We're operating in an engineering space here where there's absolutely zero margin for error. As our source explicitly points out, minor defects may propagate into significant offshore integrity concerns. Fabrication quality isn't just about making the structure look nice, it is literally a critical determinant of survival. Because one minor defect, just a single bad weld or a slightly misaligned node, could easily escalate under the immense pressure of the ocean into a massive, catastrophic offshore failure. The stakes are just incredibly high. So, to prevent any sort of life-or-death disaster, quality assurance isn't just a quick final check before shipping. It's this ongoing, almost obsessive process.
QA personnel are always on site, meticulously verifying a bunch of critical factors. They track material traceability to make sure every single piece of steel is exactly what it claims to be. They check welder qualifications, ensuring only certified experts are fusing the structure together. They verify strict dimensional tolerances, getting it right down to the millimeter. And they scrutinize the outcomes of non-destructive examinations, basically peering inside the solid metal to catch hidden flaws before they turn into fatal errors. Even after all that, before any module is even allowed to be transported out to the ocean, it has to run a final, rigorous gauntlet. Modules go through comprehensive final inspections. They get hit with one last round of non-destructive testing. Protective coatings are applied, which we're going to talk about in just a sec. And wherever feasible, the teams do what's called partial pre-commissioning. That essentially means they turn the systems on and run them while they're still safely sitting there in the construction yard. Let's head into our final section, Section 4, Surviving the Aggressive Ocean. Look, before these massive steel structures ever touch the water, they have to be heavily armored. Particular attention is given to what's known as the splash zone exposure. This is the critical area of the platform that sits right at the waterline, meaning it takes the absolute most brutal beating from crashing waves, rising tides, and highly oxygenated saltwater. So the specialized protective coatings they apply here aren't just your standard paint job, right? They are heavily engineered chemical barriers designed to fight off an aggressively hostile marine environment. But here's the thing. Chemical barriers just aren't enough on their own. Alongside those protective coatings, engineers incorporate something called cathodic protection systems directly into the platform's design. This is just a brilliant piece of engineering defense. Basically, cathodic protection uses an electrical current or sacrificial metals to make the structure itself actively resistant to rust. It's an ongoing, built-in system designed specifically to reduce the long-term risk of ocean corrosion. Which leaves us with a pretty profound thought. Considering the immense, frankly mind-boggling effort required just to build, test, and protect these onshore modules before they even see a drop of salt water, we really have to ask ourselves, can human engineering ever permanently conquer the ocean? Or are all of these magnificent innovations, the cathodic protection, the zero-defect modular construction, merely delaying the inevitable rust? It's a fascinating question to ponder. Thanks for joining me for this explainer. I really hope it gave you a whole new appreciation for the massive, meticulous science behind offshore platform fabrication.
Welcome to the quiz section, Fastest Finger Edition.
Please like, share, and subscribe to Master Sense by Faraday, and turn on notifications so you don't miss new and upcoming videos. Drop a comment below and tell us what you'd like to see next.